Hello everyone, a very good evening to you all. Today I'm here with the topic Aldehydes and the Ketones, the part 2. So if you are watching the videos, please put a like, press the like button and also subscribe if you really like our videos. Keep supporting us, guys. So in the previous class, we discussed something about aldehydes and the ketones and a couple of methods of preparation as well as the reactions of aldehydes and the ketones. So we are continuing with the same topic today, and we are here. In the previous class, we discussed about how aldehydes and ketones um, react with HCN. Also, how do they react with sodium bisulfate and all. So today we are going to see how they react with alcohols. So if you treat the aldehyde, that's RCHO, and the ketone with alcohols, so what happens during the reaction is first you get hemiacetal, and then which gets converted to acetal with one more molecule of alcohol, which reacts with the hemiacetal, forming the acetal. Whereas if you take the ketone, it reacts with two molecules of alcohol, resulting in the formation of ketal. So how this reaction proceeds? We know that this particular reaction, this is a negatively charged one, and this is partially positive because of, or this is positive because oxygen is more electronegative, so this attacks here and the bond shifting takes place, resulting in the formation of RCC, RCH, and OR gets attached to this carbon. Double bond has been shifted. Now that takes the H and you get OH. And if you treat it with one more molecule of ROH, say you can remove water from here. This is the simplest way to denote, and R gets attached over here, resulting in the formation of acetal. If you do the same reaction with the ketone, it results in the formation of ketal. The difference is here you have aldehyde in the acid, here you have hydrogen in the acetal, and in case of ketal you have the methyl groups or the alkyl groups over here. That's the difference. Rest, they react in the same way. With thiols, what do you mean by thiol? In case of O, that's alcohol, ROH, O is replaced by the sulfur, so you get thioalcohol or the thiol. So how do aldehydes and the ketones react? So you take the thioalcohol, and the reaction proceeds in the same way. So this I can give a minus sign, and this is a say this is a positively charged. Then this will go and attack over here, resulting in the shifting of the bond. And if you treat it with one more molecule of the same thiol, then you get mercaptal. This is called as mercaptal, where O is replaced in the acetal is replaced by sulfur. When it is oxidized, if you use the oxidizing agent for the oxidation of this compound, that results in the formation of SO2R. Whereas if you take the ketone and carry out the same reaction, you get the same type of products, but here it is thioacetal and here it is thioketal. When it is oxidized, you get the sulfones of the compound, where the difference lies only here. Rest, both of them react in the same way. So the reaction of alcohol and the thiol, you can't distinguish between the aldehyde and the ketones using this test because they react in the same way. So we go to the next reactions. Reaction with sodium alkanide. So whenever you say sodium alkanide, we know that the alkynes, they possess acidic hydrogen. When this is treated with sodium, one of the hydrogen, or you can even replace both the hydrogens, that results in the formation of disodium alkanide. So this gets replaced by Na, so you get C minus and the Na plus. This is sodium alkanide. When you treat it with an aldehyde or the ketone, for example, if I take RCHO, this is negatively charged, this comes and attacks over here, which is positive, and this shifting takes place, resulting in the formation of, I'm writing it over here, R, C, this bond has been shifted, so this gets O minus charge, and H was already there too. This is a place where this attacked, so you get C triple bond CH. This is a compound you are going to get. And when you acidify it, and since Na is in the plus form, and if when you acidify it, Na will go with Cl, resulting in the formation of RCH OH and C triple bond CH. So you have alkyne group as well as alcohol group. So this is called as acetylenic alcohol. And the ketones also react in the same way, but you get the alkyl groups over here. This is a reaction of sodium alkanide with aldehyde and the ketone. Then with the Grignard reagent, how do these react? We know that in case of Grignard reagent, this carries a delta positive charge and this carries a delta negative charge. So this goes and attacks the carbonyl carbon and the bond shifts now. So this results in the formation of CH3 getting attached to this carbon. I think I'm making it clear. So this CH3 goes and attacks this carbon and this bond shifts. So this gets some negative charge. The negative charge MgI just attaches. So this is negative, this is now positive. If you take and on hydrolysis, say hydrolysis is nothing but you add H and OH, H will go with this and MgI will go with OH, resulting in the formation of CH3, CH2, OH, that is a primary alcohol, and MgIOH. If you carry out the reaction for aldehyde, say you take CH3, CHO, that's acetaldehyde, CH3, C double bond H, and if you treat it with methyl magnesium bromide, then the methyl group will go and attack here. This shifts here. As a result, what you get? CH3, C, H was already there. I'll write it this way. And one more CH3 attaches here. And this bond shifts result in the formation of O minus, to which MgBr gets attached. Now on hydrolysis, HOH, I'll write. This will take up this and this will go with this. As a result, you get CH3, CH, OH, and CH3. This is a secondary alcohol. So on treatment with the Grignard reagent, primary alcohols will be formed from aldehydes. If you take the aldehyde, you get the primary alcohol. If you take the ketone, you get the if you take the formaldehyde, you get the primary alcohol. If you take the I'm changing it. Yeah. If you take the acetaldehyde and you carry out the same reaction, that results in the formation of secondary alcohol. And if you take the ketone, so how the reaction proceeds? This shifts over here and this shifts here, resulting in the formation of CH3, CH3OMgI. And when you hydrolyze it, this part goes with the OH from water, and here H gets added, resulting in the formation of tertiary alcohol. So the formaldehyde forms the primary alcohol and the acetaldehyde forms the secondary alcohol, whereas the ketone that forms the tertiary alcohol. This is how the aldehydes and the ketones react with the Grignard reagent. Then we go ahead with the Clemenciens reaction. How this reaction proceeds? The aldehydes which do not contain alpha hydrogen. What do you mean by alpha hydrogen now here? So this is CH. This is how you write. So if this aldehyde doesn't contain alpha hydrogen, that will react with a base, strong base, say concentrated NaOH or the KOH. Then you get the carboxylate salts along with the formation of alcohol. This is called as the Clemenciens reaction. So it's like a redox reaction, while where one of the aldehyde molecule gets oxidized and the other molecule gets reduced. How this reaction proceeds? Let us see. So if you want to write the mechanism of the reaction, we'll start with the HCHO, that is nothing but the aldehyde, in the presence of a base, that's OH minus. This comes and attacks this carbonyl carbon, as carbonyl carbon is positively charged, and the shifting takes place. This shifting will happen, resulting in the formation of H, C, and this is H, this is OH, and O minus. I think you get it. The bond shifts here. And this is a reversible reaction. Rapid reversible reaction. Now, in the second step, what happens is the hydride shift will take place. This is step 1. I'm writing it as 1. In the second step, the hydride shift will happen. What is hydride? It is H minus. Shift will be happening. How does it happen? So if you take this one, starting from the same compound, CO minus and H and OH. Now, if you take one more molecule of aldehyde, that's CHO, then the hydride shift, this shifts here, this bond. So the entire, this will go with this bond and this attacks this carbon. As a result, this will move and you get the compound HC. Now this one bond has been shifted. So this is OH plus, I think it's clear to you now. And now what do you get? Because of which I'll repeat it again so that it will be clear to you. Yeah, so this bond shifts here and this hydrogen now, this goes to the next aldehyde, C double bond O, H and H. Now since this goes on attacks here, this will move. So what is that you're going to get? It's H, then C, then you have OH, then you have double bonded O, then you have this molecule is over, this particular molecule is over, and the second molecule. So H has been moved to this, so H, C, O minus, and then H and H. I think it's clear. This is called as formic acid, methanoic acid, and this is alkoxide ions, methoxide ion. Now, what happens in the next step then? In the next step, what you get over here is the proton exchange will take place. I'm writing it over here. How the proton exchange will take place? You have the formic acid, that's HCOH plus this, I can write CH3O minus. I can combine this and write, right? CH3, if you see this molecule, it's CH3O. So I can write CH3O minus. Now the proton will transfer. That means this will take this proton, because of which you get H, C double bond O and O minus, to which you have Na. If you use NaOH, then you have Na. If you use KOH, then you have K, along with the formation of CH3OH. So one of the molecule has been oxidized to this and the other molecule is reduced. So this is called as disproportionation reaction, where a single compound undergoes both oxidation and the reduction reaction. So I think it's clear, and the condition for this is the Clemenciens reaction is to happen is the compound should not possess a alpha hydrogen. Okay, so we'll go to the next slide. If the molecules are same, so if you see this, both of them are formaldehyde. If the molecules are same, you have the simple Clemenciens reaction where you get the salt of the carboxylic acid as well as the corresponding alcohol. But if you have two different aldehydes, then you get a mixed Clemenciens reaction. For example, both this one, I'm unable to locate the position of the marker, so I'm changing the ink. Yeah, so this is formaldehyde reacts with benzaldehyde in the presence of NaOH. So one of the molecule gets oxidized, that forms the sodium formate, and the other one, this molecule, gets reduced to benzyl alcohol. This is called as crossed Clemenciens or the mixed Clemenciens reaction, where you have more than one type of aldehyde reacting. And then we have the next reaction where you have the acetaldehyde as well as the formaldehyde reacting in the presence of a base. So you have to explain the mechanism. How do you explain the mechanism in this case? What are you supposed to do now? What is CH3? This is a task for you which you can take as assignment, and you can put the answers in the comment section if you can, or post the photo. Okay, we'll go with the next one. The replacement of alpha hydrogen atom. So you know what exactly alpha hydrogen, right? This CO is the functional group over here. The immediate carbon to, if it is attached to hydrogen, if the immediate carbon has the hydrogen, then it is called as alpha hydrogen. This is the alpha carbon which is next to the functional group, and the hydrogens attached to that carbon are called as alpha hydrogens. So we are going to see the reaction with halogens. The first one is the replacement of alpha hydrogen atom. Formaldehyde, say if you have this is a functional group. Attached to this there is no carbon. So if there is no alpha carbon, there is no alpha hydrogen. So it doesn't possess alpha hydrogen. So this doesn't undergo enolization reaction. If you consider the other aldehydes which possess the alpha hydrogen, for example, acetaldehyde, CH3CHO. So you have CH and H and H along with C double bond H. So this is the functional group. The carbon attached to this is alpha carbon. The hydrogens attached to that are alpha hydrogens. When this is made to react with chlorine, so what is the reaction you are expecting? How is the reaction going to proceed? So one of the hydrogen over here gets replaced by the chlorine atom, and that hydrogen will go with one more chlorine which is present in the chlorine molecule as HCl. And if you treat it with one more Cl, then again one hydrogen will go. If you treat it with one more hydrogen, then the other if you treat it with other chlorine molecule, then all the hydrogens which are present in the alpha positions, they'll be removed or they'll be replaced. This is called as chloral. So we'll take one more reaction, one more example. If I say CH3, C double bond O, CH3. This is nothing but the acetone. If you treat it with one molecule of chlorine, so this is the functional group. This is also alpha carbon, this is also alpha carbon. You can remove the hydrogens from any of this. Say I'll remove it from here. One molecule of HCl, hydrogen from here, Cl from here will go, resulting in the formation of C double bond O, C, H2, one hydrogen gets replaced by chlorine. You treat it with one more molecule of chlorine, one more HCl gets removed, so you get CH3, C double bond O, CH, Cl2, one more hydrogen goes. You treat it with one more molecule of Cl2, HCl, the loss of HCl will happen, resulting in the formation of CH3, C double bond O, C, Cl3. Okay, so this may be given in 3 different steps, or they may give like 3Cl2. You should be able to predict the product in this case. And if you have the compound, the next example I can write in different ink. Yeah, CH3, CH2, C double bond O, CH3. Instead of, this is one more molecule, that's a butanone, 2-butanone. If you are going to treat it with 3 molecules of chlorine, then all the hydrogens will go from here, resulting in the formation of CH3, C, Cl. This will be the product form. I hope you understand that. Okay, we'll move to the next compound. Say if you treat this one with one molecule of NaOH. Say I'll take this as R, this group as R, C double bond O, CCl3. That's a chloral. Okay, if I treat it with NaOH, so what is the reaction I can expect? Then Na, oh, this is this will go with this, and this will be attaching together, resulting in the formation of CH. Can you see that? Cl3, plus RCOONA. This is what we are going to get at the end if you treat this chloral further with a base. Then the replacement of oxygen atom of carbonyl group. So what happens if you treat it with PCl5, say PCl5? What happens? Now, in the place of double bonded oxygen, you have chlorine atoms, 2 chlorine atoms, and this oxygen will go with PCl3, that's POCl3, phosphorus oxychloride, resulting in the formation of dihalo compound. And if you treat it with thionyl chloride, that is SOCl2, then what is the product you are expecting? 2 chlorines will go in this place and you get S-alpha dioxide. So this is how the replacement of the oxygen atom of the carbonyl, the carbonyl oxygen or the aldehyde and the ketone takes place. Then we have the haloform reactions. One of the very important reactions when it comes to aldehydes and the ketones. So if you have the alpha hydrogen atom in the corresponding aldehyde or the ketone, if you treat it with chlorine or the bromine, these alpha hydrogens are replaced, giving rise to monobromoacetone. In this particular compound, you have the acetone, which is when treated with bromine, one of the hydrogen goes from here, resulting in the formation of monobromoacetone. And you get only 43 to 44% of the product over here. So the halogenation of the this particular carbonyl compound is possible. This particular reaction is catalyzed by acid or base. Okay, so for example, if you take the same one, how does it proceed? If this particular reaction, CH3, C double bond O, CH3, this is catalyzed by O minus. O minus will go and attack this one. So what is that you are going to get? Or how does this reaction happen? If this is a regular reaction, then this will proceed by this way. Otherwise, what I can do is, can put this as CH2 and a H. Now, the OH minus, that's going to abstract a proton from here, and this bond shifts to this carbon, resulting in the formation of CH3, C double bond O, CH2 with a negative charge, and one hydrogen is taken by this, so you get minus H2O. Now, this CH2 minus, what you can do over here is, this can be in the resonating form. So how this can be in the resonating form? This bond shifts and this bond shifts over here. As a result, you get CH3, C, O minus, and a double bonded CH2. Now you add bromine to this. So what happens? These are in the resonating form, but when you add bromine, you can add this way also, here to this negatively charged. So bromine atom is polarized, resulting in the formation of CH2Br. Say this Br gets polarized when it reaches, so you get delta minus and this one, and along with the formation of Br minus. Okay, so this particular reaction is a first order with the respect to both acetone and the base. So since the reaction, this is a slow reaction, rate is equal to K times the concentration of acetone and the concentration of acid or the base. So it is the first order with respect to both acetone and the OH minus. Then we have our next reaction, which is Aldol Condensation. So this reaction happens, unlike the Cannizzaro reaction, this happens in case of aldehydes and the ketones which contain alpha hydrogen atom in the presence of dilute NaOH. There it was a concentrated NaOH, here it is a dilute NaOH. So two molecules of aldehyde or ketone, they undergo condensation in the presence of a base to give beta hydroxyaldehyde or beta hydroxy ketones. Okay, so What do you mean by aldol? It contains aldehyde and alcohol group. So that's why it is called as aldol. So how the reaction proceeds? For example, if you take a particular reaction, how this proceeds. We'll take the first step. We have a base over here. I'll take CH2H and C double bond H. This is alpha hydrogen now. This reacts in the presence of a base. Base is OH minus. This abstract a proton and this bond shifts here. Okay. And this is a slow reaction. And you get CH2 minus and C double bond O and a H, resulting in the formation of water. This is a carbon bearing a negative charge. This is a carbanion. What happens in the next step? So base abstracts a proton. This is the first step. In the second step, the first step is the generation of carbanion. In the second step, this carbanion attacks one more aldehyde molecule. So you have CH2, C double bond H, O, and you have one more aldehyde, isn't it? Say for example, again this carbanion can be stabilized by resonance. I think you know how to write the resonance. This shifts over here and this shifts over here, resulting in the formation of CO minus and H. Okay, then now in the next step, this one attacks one more aldehyde, CH3, C double bond O, H. So what happens over here? This one, this particular negative charge, this now will go and attack carbonyl carbon and this shifts, because of which what you get? So CH3, CH, this becomes negative and this gets attached over here, CH2, CHO. And then in the presence of H plus, this takes up H, so you get CH3. I shouldn't write it in between the molecule because of the lack of space. I'm writing this way, CH2, CHO and H. Can you see OH and the CHO are present in the single moiety? So this is called as aldol. Now after this, what is going to happen? In the presence, when you heat it, say you are going to heat it, what happens over here? There is elimination of water. One hydrogen from here, one hydrogen from here will go. So you get CH3, CH, double bond, CHO. So you get a double bond in between, and this is called as alpha beta unsaturated. Aldehyde. Why it is alpha beta? This is a functional group. This is alpha position. This is a beta position. So between alpha and beta, you have the unsaturation. So this is called as aldol condensation. So the reaction proceeds. This is a base catalyzed reaction. In the presence of a weak base, that will remove a proton, or that will remove a hydrogen, not proton, remove a hydrogen from that's an alpha hydrogen from the aldehyde, resulting in the formation of carbanion. Then this carbanion will go and attack one more aldehyde, resulting in the formation of aldol, which then on heating loses a water molecule, resulting in the formation of alpha beta unsaturated aldehyde. Okay, if you take the ketone also, the reaction will proceed in the same way, and at the end you get beta hydroxy here instead of beta hydroxyaldehyde. Why do you call it as beta hydroxyaldehyde? This is a functional group, this is a alpha position, this is a beta position. At the beta position you have OH group. If you take the ketone, you get C double bond O and alkyl group over here, so this becomes beta hydroxy ketone. Okay, we have in case of aldol condensation also, we have different things, just like an zero reaction. What is it? How do you what do you say about this particular reaction? Aldol condensation is possible with two aldehydes. two aldehydes having alpha hydrogen can combine. These aldehydes can be same or different, and also this can happen between two ketones. These ketones can be similar or different, and also it can happen between one aldehyde and the one ketone, but the condition is all of them should possess the alpha hydrogen. That's it. So if it happens between the similar, if both aldehydes involved in the aldol condensation, if they are of same type, then it is simple or the self aldol condensation. And if you have different aldehydes or different ketones, or a mixture of aldehyde and ketone, then it is called as mixed or the crossed aldol condensation. So how do you write this? For example, if you take this is a self condensation. If you see CH3, so what you get, the same, this is the similar aldehydes, same aldehydes. So what you expect over here is the self condensation. Self condensation happens, here CH3CH, after that you get a double bond, and then this one. And if you take this one, this is again similar ketones. You get the corresponding alpha beta unsaturated ketone over here. If you have the mixed or the crossed aldol, then you have different products, if you can see. So first this undergoes self-condensation with itself. This also undergoes self-condensation with itself. So you get one product over here, the other product over here. And after that, this reacts with this, so you get the third product, and this reacts with this, so you get the fourth product. So I think it's clear. We'll take an example and we'll proceed. That's how you'll be able to identify. CH3CHO plus, that's acetaldehyde or ethanol reacts with propanol. So this is called as crossed aldol. Two aldehydes which are involved in the reaction are different. So what are the possibilities? The first possibility is OH minus plus CH3 CHO that takes up a proton from here, resulting in the formation of CH2 CHO. This reacts with one more molecule of the same kind, that's CH3 C double bond OH. Now this will go and attack here, resulting in the formation of, this will shift over here. So you get CH3 C OH H and a CH2 CHO. When you heat it, OH from here will go, H from here will go, resulting in the formation of CH3 CH double bond CH CHO. This is one of the product. I'll change the ink for all the products. And the second compound, OH minus, takes up a proton from the, will go for the second one, that's a propanol. CH3 CH alpha. So this hydrogen will be gone, resulting in the formation of CH minus CH3 CHO plus one more molecule of the same kind, that's CH3 CH2 CHO. If you take the same compound, same type of compound, this will go and attack over here, and this will shift. As a result, what is that you are going to get? CH3 CH2 COH and a H, and then from here it is CH CH3 CHO. When you heat this compound, here also the heating is missing. When you heat this compound, what is that you are going to get? CH3 CH2 CH double bond C and CH3 over here and a CHO. Now these two are the self condensations. If these two are the self condensation products, we'll do the cross condensation. Whenever you do the cross condensation, first the carbon ion is generated, CH2 CHO, that will attack the molecule, that's CH3, the second molecule. C double bond HO. When this attacks over here, this shifts, resulting in the formation of CH3, CH2, COH, H, CH2, CHO. And this on heating loses the water molecules to give CH3, CH2 and CH double bond CH, CHO. And the last one over here. We'll take a alpha hydrogen from this CH3, CH. This is a negatively charged now. Base abstracted a proton from here. This reacts with CH3, C double bond O, H, and this will go and attack over here, resulting in the formation of a compound that's CH3, COH, H, and CH, CH3, CHO. Now this will, on heating, this will lose a water molecule, resulting in the formation of CH double bond C, CH3, and CHO. So if you see, none of the products are of same type, right? So these are the crossed products. So two self-products, self-condensation products, and two cross products will be obtained in this aldol condensation. Then we move on to the next reaction. Give me a minute. If anyone has if anyone is watching, let me see if anyone has posted their doubts or anything. Yeah, here we go. We'll move to the next one. Oxidation reactions. When the oxidation reaction happens, it can happen in the presence of the acidic potassium dichromate, which is a strong oxidizing agent. So if you oxidize the primary alcohol, here OH is attached to a carbon, which is primary carbon. When you oxidize it, say this is how you write alcohol. So these two hydrogens will go. That's what oxidation is, a removal of hydrogen, and this bond shifts here, resulting in the formation of an aldehyde. And when this is further oxidized, RCHO, and oxygen is introduced over here, resulting in the formation of carboxylic acid. So if you take the secondary alcohol, so what is that you are expecting? So hydrogens from here will go when you oxidize it, resulting in the formation of ketone. So primary alcohols will give you aldehyde, whereas the secondary alcohol will give you a ketone, which on further oxidation, this will break into two parts like this. So CH3, CH2, this gets converted into COH, and CH3, COH. This is how it breaks. So if you have, I'm not writing any, this is again a secondary alcohol. So if you are going to oxidize it, what is that you are going to get? First, hydrogen from here will go, hydrogen from here will go, resulting in the formation of a ketone. And then when you further oxidize it, this is going to break this way. How is it going to break? This way. So this will be one product. COH will be one product, and this side it is COH. Rest of the valences you can satisfy with the hydrogens. Then if you take the tertiary alcohol, if it is a primary and the secondary, they react immediately. And if you take the tertiary alcohol, this is not going to be oxidized very quick, but it takes some time to get oxidized. So the primary and the secondary alcohols, they get converted to orange color, to green. I mean, if you take the potassium dichromate, which is orange in color, the primary and the secondary alcohol turn that into green. This you might have seen in case the traffic police, they have orange color solid, that is a potassium dichromate. If any person is say he's a drink and drive case, then they ask you to breathe to that mixture. That mixture, if you have consumed the alcohol, which is a primary alcohol, that will immediately turn the potassium dichromate to green. This is how they detect if a person has consumed alcohol or not. Then the reduction. When it comes to reduction, we know that reduction is the removal of oxygen or the addition of hydrogen. Both can happen. So when a ketone or the aldehyde is heated, if you take the hydrazine, what is hydrazine? So aldehyde or ketone, so C double bond O R. And if you treat it with NH2 NH2, hydrazine. So what is that reaction you are expecting? In the presence, here, the hydrogen is formed, which unfold the reaction with the base that results in the formation of this particular group gets converted to, the hydrogens get added to this particular group. So this is how you can convert an aldehyde or the ketone to the corresponding hydrocarbon. Then we have the Clemenciens reduction. The Clemenciens reduction also starts with the aldehyde and the ketone, but you use a different reducing agent. The first one is called as Wolff-Kishner reduction, and the second one is called as Clemenciens reduction, where you use the zinc mercury amalgam in the presence of HCl. So what happens when you treat it with zinc mercury amalgam? This group, the CO, the aldehyde or the ketone carbonyl group, that gets converted to the corresponding the hydrocarbon or the methyl group, methylene to be specific. So since you can oxidize the aldehyde, so how do you oxidize the aldehyde? Aldehyde can be oxidized to the carboxylic acid. So this is a one which undergoes oxidation. This undergoes oxidation. So the something which undergoes oxidation must be a reducing agent. Since they undergo oxidation easily, these are the strong reducing agents. So how do they act as reducing agent? We have to see. So first you take the Tollens reagent. Okay, ammonical silver nitrate. This is called as Tollens reagent, ammonical silver nitrate. So when you mix silver nitrate with ammonium hydroxide, you get the ammonical silver hydroxide solution. When it is treated with aldehyde, this particular group RCHO, this gets oxidized to the carboxylic acid, whereas Ag is in the +1 oxidation state, that is reduced to Ag, which is in the 0 state. So the silver precipitates over there. So the aldehyde gets oxidized, whereas the silver that gets reduced, and that forms the silver mirror in the sides of the test tube. So if you really see, this is how it looks. So you take a solution of aldehyde, you mix it with the Tollens reagent and heat on a water bath for some time. When the reaction is complete, you get to see this, where the silver mirror, the silver coating is seen in the sides of the test tube. This particular reaction is shown by aldehyde but not by the ketones. Because if you take the ketones, you can't oxidize them into the mild agents, like mild oxidizing agents like the silver or the Tollens reagent can't act on the ketones. Then we have the Fehling solution. In the Fehling solution, you have two types. One is Fehling solution A, the other one is Fehling solution B. So the Fehling solution A is a aqueous solution of the copper sulfate, which is blue in color, and B is potassium tartarate and mixture of NaOH. So if you mix both A and B solutions, you get a dark blue colored solution. That means if you treat aldehyde, aldehyde gets converted into carboxylic acid, where you have the cupric, that's a CO2 plus oxidation state, that gets converted to cuprous salt, that's +1. So copper undergoes reduction, whereas the aldehyde undergoes oxidation. Now, blue, how do you get to know that the reaction is happening? The blue color of the solution, that's in copper 2 plus state, that gets converted to red, that's where you can say the reaction has been happened. So if you see the reaction, this is the Fehling solution. If you treat aldehyde with this, then aldehyde gets converted to the carboxylic acid, and the CO2 plus changes to CO +1. This is the red color precipitate or red color solution will be seen. So this is also a positive test for aldehyde. And then Benedict solution. So the Benedict solution is again a mixture of copper sulfate, sodium citrate, and the sodium carbonate. So again, here also you get to see the same type of reaction. The copper 2 plus gets converted to copper plus 1. That changes the color. Then you have the mercuric chloride test. Mercuric chloride is corrosive sublimate. Generally, you don't do it in the lab. So aldehyde, mercury is in the +2 state over here. When you treat aldehyde with the mercuric chloride, this gets converted to +1 state. That's called as calomel. Mercurous chloride. You get a white precipitate of this. This indicates the corresponding compound, what you treated with is an aldehyde. Okay, and this particular one, Hg2Cl2, that's a calomel. If this is further treated with an aldehyde, you get a black precipitate where the aldehyde gets again converted to carboxylic acid. Then the reaction with the Schiff's base. It's a dilute solution of p-rosanilin hydrochloride, or it is also called as magenta dye. So it is a pink color solution. And if you treat, if you pass SO2 gas through the Schiff's reagent, then you get a colorless solution. Hope it's clear to you. This is called as Schiff's reagent. Now through this colorless solution, it was pink in color when it was rosanilin hydrochloride. You pass SO2, this is colorless. Again you pass or you add aldehyde so that the pink color is restored. This reaction can be seen for aldehyde. So the aldehyde can restore the pink color of the solution. So these are the positive tests which you can carry out in the laboratory for the presence of aldehyde, where aldehyde acts as a reducing agent and it gets oxidized to carboxylic acid. Then the reaction of ketones only. Instead of, if you remember, the Clemenciens reduction where you use zinc mercury amalgam. Here, in case of reduction, there you converted a C double bond O group to CH2 group. That's a carbonyl group to methylene group. If you take the reduction of the compound, acetone is reduced by magnesium amalgam. You are taking magnesium and the mercury. That's magnesium amalgam and CH3. These particular groups get oxidized. Get reduced. And you get OH. This is called as pinacol. This again rearranges to get pinacolone. Okay, and the reaction with chloroform. When you treat a ketone with the chloroform, what is that you are expecting? CHCl3. This forms CCl3. So if this goes and attacks over here, this shifts here, that H is taken by this, so you get this. When you treat it with aqueous sodium hydroxide, then this will go resulting in the formation of carboxylic acid. This is hydroxy acid. Then reaction with nitrous acid. So nitrous acid with the ketone, this will reduce the ketone to imino compound. And the imino is C double bond N, imino compound. Then the oxidation reaction. So there is a rule called as Popov rule. C double bond O. If you oxidize the compound, C double bond O group stays with the smaller alkyl groups. So when you oxidize this, this will remain with this one, smaller alkyl, because this is a smaller alkyl, this is a bigger alkyl. So this gets converted into CH3COH on oxidation, and this is CH3CH2. This H2 gets converted into a carboxylic acid again. Then we have very important reactions where some of them are the named reactions. So what is that you are going to get at the end of the reaction is what you have to see. So what are the products or what are the reactants you are expecting over here? First one is the Gataman reaction, and you have also Gataman-Koch reaction. So in one of the reaction, this is the Gataman reaction where you are treating the benzene with HCl or HCN in the presence of a Lewis acid, which is aluminum chloride. And a chemical reaction where the aromatic compound, this benzene, is formylated. You are going to formylate. You are going to add CHO group to that by treating it with the hydrogen cyanide and the hydrogen chloride in the presence of a Lewis acid catalyst. Okay, so what you are going to do here, aluminum chloride, say if so you get Cn minus, that gets substituted to the ring, as Cn minus, then you are going to treat it hydrolyze so that you are going to get a benzaldehyde. And you give some modification over here where you instead, here you are introducing carbon monoxide instead of hydrogen cyanide, resulting in the formation of the same compound, which is called as Gataman coach aldehyde synthesis. We'll move on to the next named reaction, the Rosen1 reduction. In case of Rosen1 reduction, you do the hydrogenation, you add hydrogen, you reduce the compound, where you take the acid chloride, and this is treated with palladium over barium sulfate catalyst. And what happens, you add, this will go and you add H over here. So one HCl will be gone, you get aldehyde. Then you have stiffened reaction, where the preparation of the aldehyde, you start with the nitrile, that's cyanide compounds, RC triple bond N, and you reduce it in the presence of tin chloride and hydrochloric acid, where you get, what happens when you reduce it? R CH double bond NH is what you get. And if you further treat it with one more molecule of HCl, so you get RCH double bond NH2 plus and a Cl minus. When you hydrolyze this one, you treat it with water, you get RCHO, and this compound will go like ammonium chloride. It will be gone as ammonium chloride. This is called a stiffened reaction. And we have some condensation reactions. Say if you take the aldehyde and the ketone, they undergo condensation reaction. This is already discussed. And we have the Hydride reaction over here. In the Hydride reaction, you are going to use this chromyl chloride, which you use for chloride detection. So toluene, you have the aromatic compound or the methyl group, which is bound to the aromatic system or the heterocyclic system as well. If you are oxidizing it in the presence of chromyl chloride, and then what is that you are going to get, the hydrogens will be removed and you are going to add the oxygen for this. So the toluene is getting converted to benzaldehyde in this particular reaction. This is how you carry out the Hydride reaction. So we have the next questions over here. The reagent with which both acetaldehyde and the acetone react easily. So the Fehling solution, Skiff's solution, and the Tollens reagent, they react with aldehyde only, not with the ketone. So the one which reacts both with aldehyde and the ketone is a Grignard reagent and not the other ones. The enolic form of acetone. So first you have to write the ketone. This is keto form. Whenever you say enolic form, you have CH3, C, OH, and double bond CH2. Hope you get it. So this takes a proton from here and the double bond shifts here. So this is the enolic form. So how many bonds are there? See, there is only one pi bond. So go with only one pi bond options. And how many lone pairs are there? The two lone pairs are there for oxygen. So 1 pi bond and 2 lone pair and 9 sigma bonds. So there are 3 sigma bonds here, 3 plus 1 sigma bond here, 4, and the 5th one, 6th one, 7th one, 2 here, 8th, 9th one. So 9 sigma bonds, 1 pi bond and 2 lone pair of electrons. This we already discussed, benzoyl chloride. This is a benzoyl chloride. If you are going to treat it with palladium over barium sulfate, and then you are going to treat it with the hydrogen, HCl will go and this H gets added over here. This is a hydrogenation reaction resulting in the formation of benzaldehyde. That would be the right answer. Which of the following compounds with the molecular formula yields acetone on ozonolysis? So whenever you have the ozonolysis, you should get a compound with the formula C5H10. How do you get it? How is that you're going to get? So if you're looking at the video, you can always put the answer in the comment section. What exactly? Cyclopentane. It's not, definitely not cyclopentane. Okay. Then you start with 3-methyl 1-butene. I'll start with the first compound, 2-methyl 2-butene. So when you do the ozonolysis, what is that your acetone you should get? So when you do the ozonolysis, you add ozone like this. Ozone gets added over here. Then you break the bond symmetrically like this. And what's that you're going to get? Can you see this? This is O. So here, C double bond O, CH3, CH3. And here, this side, it is C double bond O, H, CH3. So the acetone will be given by 2-methyl 2-butene. You can always check the other ones as well. Okay. So that's how we end this today's session. Thank you.